Course title Geology. Paper title Economic Geology and Mineral Resources of India. Topic of the lesson: ore deposits associated with intermediate to felsic igneous rocks. Part 4. Hydrothermal vein deposits. Objectives: to understand the mode of occurrence of cavity filling and replacement type hydrothermal deposits in the field. Regional, district level and ore body zonation exhibited by them. Characteristic features of three classes of hydrothermal deposits, that is, hypothermal, mesothermal and epithermal deposits, and diverse genetic processes involved in their formation. Introduction. As a class, vein ores are extremely heterogeneous, varying enormously in constitution, size, form, geological environment, and origin. The majority of veins have probably formed from uprising hydrothermal solutions which precipitated metals under environments extending from near magmatic high temperature, high pressure conditions to near surface low temperature, low pressure conditions. A few veins are pegmatitic and represent end-stage magmatic activity. A few are clearly volcanic sublimates. Mineralogically, gangue minerals can be the dominant constituents as in auriferous quartz veins. Quartz and calcite are commonest gangue minerals, with quartz being dominant when the host rocks are silicate and calcite with carbonate host rocks. This suggests derivation of gangue material from the wall rocks. Sulfides are most commonly the important metallic minerals, but in case of tin and uranium, oxides are predominant. Occasionally, native metals are abundant, especially in gold and silver-bearing veins. Vein deposits show a great variation in all their properties. For example, vein thickness can vary from a few millimeters to more than 100 meters, and as far as environments are concerned, veins can be found in practically all rock types and situations, though they are often grouped around plutonic intrusions. Mineralogically, they can vary from monomineralic to extensive assemblages, sometimes involving over 30 minerals. Zoning. Zones may be defined by changes in mineralogy of ore or gangue minerals or both, by changes in the percentage of metals present, or by more subtle changes from place to place in an ore body or mineralized district of the ratios between certain elements, or even the isotopic ratios within a single element. Zoning was first described from epigenetic vein deposits, but it is also present in other types of deposits. For example, skarn deposits often show a zoning parallel to the igneous sedimentary contact. Syngenetic deposits may show zoning parallel to a former shoreline, as in the case with the iron ores of the Mesabi Range, Minnesota. Some exhalative syngenetic sulfide deposits show a marked zonation of their metals. Epigenetic hydrothermal zoning. Zoning of this type can be divided into three intergradational classes: regional, district, and ore body zoning. Regional zoning occurs on a very large scale, often corresponding to large sections of orogenic belts and their foreland, Figure 1. District zoning is the zoning seen in individual ore fields such as Cornwall, England, Figure 2, Flat River, Missouri, Figure 3, and the Copper Canyon area, Nevada, Figure 4. Ore body zoning takes the form of changes in the mineralization within a single ore body. A good example occurs in the Emperor Gold Mine, Fiji, where vertical zoning of gold-silver tellurides in one of the main ore chutes gives rise to an increase in the silver-gold ratio with depth. A comprehensive discussion of zoning with many examples is given in Rowther 1963. Some examples. The following paragraphs provide details of the few selected hydrothermal vein deposits belonging to hypothermal, mesothermal, and epithermal classes of Lindgren, 1933. Some examples. Hypothermal Archean gold deposits. Several big and small gold deposits are found in Archean greenstone terrains all over the world. Prominent among them are Golden Mile at Kalgoorlie, Western Australia, the Kola Gold Field of India, and Kirkland Lake and Timmins area, Ontario, Canada. These deposits have several features in common. Size and grade. The gold-bearing greenstone belts of the Archean Superior Province of Canada and the Ilgran Block of Western Australia contain 100 to several thousand individual gold deposits. Such greenstone belts contain several large deposits, often with one or more giant districts or camps. Example, the Superior Province with 25 ore bodies, each containing about 45 tons gold. Grades of mined ore vary even within individual camps. At present, most underground mines are yielding ores with 4 to 8 ppm gold, and open pit mines are exploiting ores with grades as low as 1 to 2 ppm. Host rocks and structural control of mineralization. These deposits are usually present in green schist facies terrains, Figure 5, in a brittle ductile transition regime. The original rocks are very variable, but the dominant hosts in the entire world's Archean cratons are tholeiitic pilobasalts and komatiites and their pyroclastic equivalents and felsic to mafic intrusives. Gold mineralization is associated with laterally zoned wall alteration halos whose formation involved metasomatic addition of SiO2, K2O, CO2, H2O, and gold. As the structural control of mineralization changes from more widely spaced faults or fractures to closely spaced minor fractures, the deposits shade into one of the types of disseminated gold deposits. In these deposits, many vein sets have been recognized as being commonly strata-bound and often confined to competent less basic basaltic units in metamorphosed tholeiitic komatiitic sequences. The physical properties of these rocks have favored hydraulic fracturing and fluid access, and their mineralogy and geochemistry have controlled gold deposition within the veins. The gold-bearing host structures appear to be related to movement on regional and transcraton shear zones with different structural styles of mineralization resulting from variations in the orientation of the regional stress field and the strength of the host rocks. The common hosts are cross-cutting or layer parallel shear zones, strike extensive laminated quartz veins, extensional quartz vein arrays and/or breccias. This variety of structural styles is illustrated in Figure 5. The best mineralized terrains with a high density of anastomizing, oblique to strike slip, transcraton and regional shear zones often control the geometry of adjacent subsidiary mineralized structures. These high-strain zones focus fluid flow in an otherwise regionally low-strain greenstone belts. Gold mineralization tends to occur where these structures are associated with regional carbonation, carbonatization, and emplacement of swarms of minor intrusions of porphyries and lamprophires. Genesis. Gold mineralization resulted from highly focused flow of low salinity, water and carbon dioxide fluids along regional shear zones with transient flow into adjacent brittle ductile structures as a result of lowering of pressure during failure. Gold precipitation appears to have occurred as a result of fluid wall rock reactions, particularly the sulfidation of iron-rich host rocks of phase separation within the fluid. With regard to the source of gold, two views are in vogue. A. Orthodox hypothesis of the magmatic hydrothermal origin of mineralizing solutions, and B. Metamorphogenic fluids which major constituents of ore derived from a deep source region. Burrows et al. 1986 made use of carbon isotope data from two of the world's largest Archean gold vein and shear systems of Hollinger, McIntyre in Canada, and the Golden Mile in Western Australia to support the hypothesis of magmatic hydrothermal origin of the ore-bearing solutions. Siddhaya and Rajamani 1989 have used evidence for rare earth element patterns, oxygen and lead isotopes to support the application of this hypothesis to gold deposits of Kola Goldfield, India. Hattori 1987, based on his studies on Canadian and Australian Archean gold deposits, proposed a magmatic hydrothermal origin for Archean greenstone belt hosted gold deposits. Several workers, including Fife and Henry 1973, Yardley 1983, and Cox et al. 1987, favor metamorphogenic fluids as the source for gold mineralization of the Archean terrains. They consider the regional metamorphic terrains as large hydrothermal systems, and these systems have the capacity to leach a wide range of components, including ore-forming materials, from a very large volume of crust. If the fluid flow of the dehydration water is channeled through a small volume of rock in which dilatant zones develop, mineral deposits may be formed. Fife and Henry showed that a source region of 30 cubic kilometer could have provided all the gold, silica, and water required to form a deposit as large as Morro Velho, Brazil. Figure 6 shows mode of development of metamorphic fluids and their migration depositional site of gold mineralization. Butte, Montana, a mesothermal ore field. Butte, the richest hill on earth, is one of the most famous vein mining districts. Between 1880 and 1964, Butte produced 300 million tons of ore containing copper, zinc, manganese, lead, silver, and gold, together with significant amounts of bismuth, cadmium, selenium, and tellurium. Butte, measuring 6 by 3 kilometers, has scores of mines. In the Butte field, veins occur in a 78 million year old granodiorite. There are two mineralization stages, pre-main and main. The pre-main stage consists of small quartz veins carrying molybdenite and chalcopyrite. These veins are found in the deeper central part of mineralized zone. They are bordered by alteration envelopes carrying potash feldspar, biotite, and cerisite. Biotite has been dated at 63 million years. The main mineralization stage occurs in several vein systems, of which the most important are the easterly trending Anaconda and younger northwesterly trending blue veins, figure 7. The Anaconda veins were the largest and most productive, averaging 6 to 10 meters in thickness, with local ore pods up to 30 meters thick. Anaconda veins divide into myriads of closely spaced southeasterly trending minor veins. This is called horse-tailing and is suitable for open cast mass mining methods. The blue veins usually offset the Anaconda veins with a sinistral tear movement, and sometimes the ore has been dragged from the Anaconda veins into the blue veins by this fault movement. Individual ore shoots persist along the strike and in depth for hundreds of meters. All the veins contain similar mineralization and exhibit zonation, figure 8. There is a central zone of copper mineralization which at depth contains the quartz molybdenite veins of the pre-main stage. This gradually gives way outwards to intermediate zone consisting of chalcopyrite with minor amounts of sphalerite. The outer peripheral zone principally contains sphalerite, rhodochrosite with small quantities of silver. All the veins are bordered by zones of alteration, which is usually represented by sericitization next to the vein, followed outwards by intermediate argillic alteration and then by propylitisation. In deeper parts of Butte, advanced argillic alteration is present next to the veins. Cerisite produced by this alteration dates at 58 million years, distinctly later than the biotite of pre-main mineralization. The zoning suggests that the main mineralization was affected by hydrothermal solutions which passed upwards and outwards during a long period of time through steadily evolving fracture system. Brimhall, 1979, has demonstrated that the mineralization of the pre-main stage consisted of widespread, zoned, low-grade, disseminated copper molybdenum mineralization of porphyry type formed at 600 to 700 degrees centigrade. During the later main stage mineralization, A geothermal system involving hydrothermal fluids of meteoric origin was possibly set in motion by a younger intrusive system and achieved temperatures of 200 to 350 degrees centigrade and leached much of the disseminated copper, redepositing it to form the rich vein ore bodies. Butte is an excellent example of mesothermal mineralization superimposed on older hypothermal mineralization. The La Lagua tin deposits, Bolivia. Bolivia possesses the greatest known reserves of tin outside the countries of Southeast Asia, most of her reserves being in vein and disseminated deposits. The Bolivian tin field extends along the Andean ranges east of the high plateau of Bolivia from the Argentine border northwards into Peru, figure 9. Northwest of Oruro, the deposits are mainly tin and tungsten veins associated with granodiorite batholiths. The batholiths range in age from Triassic to Miocene, with the Miocene ones being best mineralized. South of Oruro, figure 9, there's a tin-silver association spatially related to high-level intrusions. At some of these volcanic centers, both intrusives and the coeval volcanics are preserved. At others, erosion has removed the volcanics, completely leaving only the intrusives. This is the case at La Lagua, the world's largest tin mine working primary tin deposits. The mine occurs in the Salvadora stock. The stock, which is made up of xenolithic and highly brecciated porphyry, narrows with depth. The original texture and rock composition, probably quartz latite, are obscured by pervasive alteration. The ubiquitous brecciation has produced an increased permeability of the stock, which has given rise to alteration and dispersed mineralization independent of the geometry of the later vein systems. Alteration has produced a host rock consisting of primary quartz, tourmaline, sericite, and secondary quartz. There is a network of veins in and around the stock, some of which are shown in figure 10. The major veins trend about north 30 degree east and appear to form a conjugate system of normal faults. They are typified by the San Jose type, which generally has a dip of 45 to 80 degrees, good width, average 0.6 meters, and strike persistence. These are richest veins and can contain up to 1 meter of solid cassiterite. Clay gauge is very common. The Serrano vein type, not shown in figure 10, is much thinner, nearly vertical, and impersistent. These narrow veins are also richly mineralized and may have formed in vertical tension gashes associated with normal faulting. In the La Lagua deposit, the first stage of mineralization consisted of the formation of crusts of quartz, followed by bismuthinite and cassiterite. Wolframite and tourmaline also belonged to this early stage. This was followed by a stage of sulfide mineralization, principally pyrrhotite and frankite. The pyrrhotite, being later, is largely replaced by pyrite, marcasite, and siderite. Arsenopyrite, sphalerite, stannite, and rare chalcopyrite were also formed during the later stage sulfide deposition. Pervasive alteration and early stage vein growth, including cassiterite deposition, took place at temperatures of about 400 to 350 degrees centigrade. The temperature dropped to 300 degrees centigrade and lower during sulfide deposition. Lalagua deposit witnessed deposition of hypothermal to epithermal minerals into the same zone. This is a case of telescoping and is attributed to the existence of high temperatures in near-surface host rocks induced by the volcanic activity and a blanket of host volcanic deposits. Epithermal precious metal deposits in volcanic rocks. Epithermal precious metal deposits confined to volcanic rocks may carry important quantities of silver as well as gold. For example, the Hishikari deposit, Yashu, Japan, discovered in 1980, consists of a vein system with veins up to a few meters wide having an average grade of 70 ppm and high silver values. In contrast, the Ladolam deposit, Lihir Island, Papua New Guinea, is a breccia-hosted disseminated deposit with ore grading 3.43 ppm gold. Most of the famous silver-gold deposits of Mexico and Peru that are hosted by terrestrial volcanics belong to this class. Epithermal precious metal deposits, based on their dominant wall rock alteration assemblages, can be divided into two classes: acid sulfate or alunite kaolinite and adularia cerussite. Haiba et al. 1986. Adularia cerussite class is by far the most common. For both classes, calderas are important as structural settings. The general setting and other details are provided in Table 1. The data provided in the table indicate their formation from near-surface geothermal systems. For these deposits, the mineralizing fluid was dominantly meteoritic with magmatic hydrothermal fluid component. Heald et al. 1987 suggested that these two different classes of deposit reflect in particular their distance from their heat source. The acid sulfate type being spatially and temporally related to a shallow hydrothermal system in the core of the volcanic dome, figure 11a. These domes often occur along or near the ring fracture faults of calderas, and as a result of this location, the mineralized zone is usually small. The heat source being the volcanic conduit. Mineralization may be capricious, but the El Indio deposit, Chile, is a spectacularly rich example with the ore in well-developed veins several meters in width. Ore grades averaging 225 ppm gold, 104 ppm silver, and 2.4% copper. Other examples of this type deposits are Goldfield, Nevada, Pueblo Viejo District, Dominican Republic. Mineralization in the acid sulfate type deposits is characterized by high sulfur fugacity, which produce the extensive alunitization and enargite pyrite covellite assemblage in these deposits. Proximity in time, age difference between host rocks and ore is less than 0.5 million years, and space of these deposits to the volcanism probably explains the high sulfur fugacity. In acid sulfate deposits, the assemblage pyrite galeno-enargite and the close association with alunite indicate an environment with relatively high sulfur fugacity. The adularia sericite type deposits having mineralization at least 1 million years later than the volcanism, being spatially unrelated to intrusive volcanics and with distinctive alteration assemblages, appear to have formed in the upper parts of geothermal systems above a deeper heat source, figure 11b. This accounts for the variety of volcanic host rocks and the broader upper part of the hydrothermal cell, which led to the development of more extensive mineralization districts. In the adularia sericite type deposits, presence of pyrite, chlorite, hematite assemblage and absence of enargite and presence of tennanite indicate lower sulfur and oxygen activity during their formation. Disseminated gold deposits. Boyle, 1979, recognized the following 4 subtypes of disseminated gold deposits. 1. Disseminated and stockwork gold-silver deposits in igneous rocks. 2. Disseminated gold-silver occurrences in volcanic flows and associated volcanoclastic rocks. 3. Disseminated deposits in tufaceous rocks and iron formations. And 4. Carlin-type deposits. Disseminated and stockwork gold-silver deposits in igneous intrusive bodies. Deposits of this subtype occur in orogenic belts in all the continents and range from Archean to Phanerozoic in age. They are mainly albite porphyries and quartz feldspar porphyries. Several deposits of this subtype are referred to as porphyry gold deposits, and some are clearly copper-deficient, gold-rich porphyry deposits. Mineralization occurs in highly fractured zone of irregular outline, which have been healed by veinlets, veins and stringers of auriferous quartz. These zones are marked by considerable hydrothermal alteration of the host rock, which varies with the rock type. In granitic rocks, the common alteration is potassic alteration, sericitization, silicification, feldspathization, and pyritization. In intermediate and basic rocks, the alterations are carbonatization, sericitization, serpentinization, and pyritization. Disseminated gold-silver occurrences in volcanic flows and associated volcanoclastic rocks. Ore bodies of this subtype have only recently been outlined. Mineralization occurs in large, diffuse volumes of alteration in rhyolites, andesites, or basalts. Reported gold values are mainly in the range of 0.02 to 0.03 ppm, but some are much richer. Example, Round Mountain, Nevada, contains 66 ppm gold. Disseminated deposits in tufaceous rocks and iron formations. Gold deposits in tuffs and other pyroclastic rocks are common in greenstone belts of the Precambrian. A popular example is the Madsen Mine, Ontario. Here, the ore bodies assume the form of echelon ore zones hosted by heterogeneous, sheared and highly altered tuffs occurring in the lower parts of the Tholeiitic-Komatiitic sequence, figure 12. The ore bodies, which were delineated by SA boundaries, had an average grade of about 8 ppm gold. Ore bodies of Triton Gold Mine, Western Australia, occurs in a similar geological environment. In the Archean greenstone belts, several large and many smaller gold deposits occur in various phases of iron formation, of which lean sulfide-bearing carbonate and silicate phases are perhaps the most important. These deposits are described as homestake-type deposits, named after the famous large and long-lived mine in South Dakota. Deposits belonging to this category are Morro Velho, Brazil, Kola Goldfields, India, Murchison Province, Western Australia, and many deposits in Zimbabwe. The Homestake mine has produced about 1,100 tons gold since it began production in 1877 and is the biggest gold mine in the USA. The ore bodies occur only in the Homestake Formation, a thin auriferous quartz sideroplacite schist unit within a thick sequence of metasediments that only contains minor metabasaltic rocks. The deposit witnessed complex polyphase folding and low to medium grade metamorphism that gave rise to considerable redistribution and concentration of gold and sulfides. The ore bodies are localized in part by dilatant zones formed by superposition of F1 and F2 folds, figure 13. The ore bodies consist of quartz, chlorite, and ankerite with pyrrhotite, arsenopyrite, and gold. Most of the chlorite appears to be altered cummingtonite or sideroplacite. Much of the quartz takes the form of metamorphic segregations, veins, and stringers. Stable isotope studies have shown that the sulfide sulfur and the oxygen of the quartz are indigenous to the Homestake Formation, and the inference is that the gold too is syngenetic. A model for the formation of these deposits was proposed by Fripp 1976, involving circulating seawater with the saline solutions debouching into basins in which banded iron formation is being precipitated, figure 14. Gold deposits hosted by iron formation in Zimbabwe had origins similar to that of Homestake, Sagar et al. 1987. Carlin-type deposits. The deposits at present being exploited or proved are mainly located in Nevada, Utah, Idaho, California. Southeastern China, Taupo volcanic zone of North Island, New Zealand, and Sinola deposit of the Queen Charlotte Islands, British Columbia. Their grade varies from 1 to 13.4 ppm gold, and mercury and silver are often won as byproducts. Ore bodies generally have SA boundaries, and their shapes vary from broadly tabular to quite irregular, with faults and favorable horizons often exerting a control on their shape and position. The most favorable host rocks of Carlin-type deposits are fine-grained, finely laminated, carbonaceous, silty carbonates, and carbonate-bearing silt stones and shales of marine origin. In the western USA, these deposits are Cambrian to Mississippian in age and occur within or adjacent to overthrust terrains related to continental margin tectonics. In these terrains, dooming of the mineralized rocks occurred and associated normal faults channeled hydrothermal solutions into favorable beds. The faulting often increased rock permeability by creating breccias, which host the ores in several deposits. Replacement ore bodies never occur far from fractures. Igneous rocks, commonly granites, sensulato, occur within or close to nearly all deposits. Wall rock alteration is marked by the development of jasperoid. It was formed before, during, and after gold mineralization and usually replaces carbonate rocks and grains, as does the introduced pyrite. Some detrital minerals are altered to new clay minerals, dickite, illite, kaolinite, during the ore mineralization stage, and following this, post-ore calcite veins were commonly developed. They may contain stibnite, cinnabar, orpiment, realgar, barite, and complex thallium minerals. Normally, only free gold is present, that is, no combined gold as tellurides, and the grain size is usually less than 1 millimicron. Gold forms films on pyrite, and amorphous carbon enclosed in silica occurs within arsenical pyrite. Native silver and electrum also occur. Pyrite, the most abundant sulfide, may be accompanied by marcasite and arsenopyrite. Mineralization persists in depth without any apparent zonation in ore mineralogy. Fluid inclusion studies indicate ore formation at depths of 2 to 4 kilometers with main stage mineralization at 200 to 300 degrees centigrade, a case of mesothermal deposits. A scheme for the formation of Carlin-type deposits is given in Figure 15. Investigators favor intrusion-driven hydrothermal cells as the mineralizing mechanism. Berger and Bagby 1991 suggest that metalliferous magmatic fluids from the intrusions become diluted by meteoric water in the contact zone and rose as an upwelling plume to deposit gold in favorable zones. In these deposits, boiling was not an important precipitation process, and presumably mixing with cooler meteoric water having a different chemistry was the mechanism of ore deposition. Summary: hydrothermal vein-type ores are extremely heterogeneous, varying enormously in constitution, size, form, geological environment, and origin. The majority of veins have probably formed from uprising hydrothermal solutions which precipitated metals under environments extending from near magmatic high temperature, high pressure conditions to near surface low temperature, low pressure conditions. Hydrothermal veins can be found in practically all rock types and situations, though they are often grouped around plutonic intrusions. In vein deposits, base metal sulfides are most common, but in case of tin and uranium, oxides are prominent. Occasionally, native metals are abundant, especially in gold and silver-bearing veins. Vein deposits may show zoning. Zones may be defined by changes in mineralogy of ore or gangue minerals or both, by changes in the percentage of metals present, or by more subtle changes from place to place in an ore body or mineralized district of the ratios between certain elements, or even the isotopic ratios within a single element. Epigenetic hydrothermal zoning can be divided into three intergradational classes: regional, district, and ore body zoning. Hydrothermal vein type deposits can be grouped into three classes according to the classification of Lindgren 1933: A. Hypothermal, B. Mesothermal, and C. Epithermal. Archean gold deposits encountered in greenstone belts of cratonic terrains belong to hypothermal class, and the source of gold of these deposits is attributed by some workers to A. Mineralizing solutions of magmatic hydrothermal origin, and others suggest B. Metamorphogenic fluids with major constituents of ore derived from a deep source region. Vein deposits of Butte, Montana, USA belong to mesothermal class and are hosted by about 78 million year old granodiorite. Base metal mineralization took place in two stages. The pre-main stage, copper molybdenum mineralization, is bordered by alteration envelopes carrying potash feldspar, biotite, about 63 million year old, and cerecite. The veins of main stage copper and zinc mineralization are bordered by zones of alteration, cerecitization next to the veins, followed outwards by intermediate argillic alteration and then by propylatization. Cerecite produced by this alteration dates at 58 million years, which is younger than the biotite of pre-main mineralization stage. According to Brimhall 1979, the pre-main stage mineralization is of porphyry type and formed at 600 to 700 degrees centigrade. The main stage mineralization, according to him, owes its origin to a geothermal system involving hydrothermal fluids of meteoric origin, which was possibly set in motion by a younger intrusive system. Ores of the main stage were deposited possibly at temperatures ranging between about 350 degrees and 200 degrees centigrade. Thus, Butte is an excellent example of mesothermal mineralization superimposed on hypothermal mineralization. Epithermal precious metal deposits confined to volcanic rocks may carry important quantities of silver as well as gold. Example: Hishikari deposit, Yasu, Japan; Lodolum deposit, Papua, New Guinea; many deposits in Mexico and Peru. Epithermal precious metal deposits, based on their dominant wall rock alteration assemblages, can be divided into two classes: acid sulfate, alunite, kaolinite, and adularia cerecite. The latter class is by far the most common. These two classes of deposit reflect in particular their distance from their heat source. The acid sulfate type being spatially and temporally related to a shallow hydrothermal system in the core of the volcanic dome. The Adularia sericite type deposits having mineralization at least 1 million years later than the volcanism appear to have formed in the upper parts of geothermal systems above a deeper heat source. For both classes, calderas are important as structural settings. Epithermal precious metal deposits were developed from near-surface geothermal systems, and the mineralizing fluid was dominantly meteoric with magmatic hydrothermal component. Disseminated gold deposits of epithermal origin can be classified into 4 subtypes. 1. Disseminated and stockwork gold-silver deposits in igneous rocks. 2. Disseminated gold-silver occurrences in volcanic flows and associated pyroclastics. 3. Disseminated gold deposits in tufaceous rocks and iron formations. And 4. Carlin-type deposits. The Carlin-type gold deposits encountered in USA, Southeast China, and New Zealand are confined to carbonaceous, silty carbonates and shales of marine origin. Their origin is attributed to intrusion-driven hydrothermal systems, and gold precipitation is attributed to mixing of magmatogenic hydrothermal fluids with meteoric water. These deposits in reality are of mesothermal category.